Hello. So today we are going to talk about the shape of a graph. What I've got here is I want to do one example. The one example I want to do is this one right here. Let f of x equal 1 plus 1 over x minus 1 over x squared. And essentially what we're going to do is sketch the graph of f, right? And we talked about, last week we talked about the characteristics of a function that we're looking at. And we talked about looking at when the function is positive, when the function is negative, when the function is increasing, decreasing, concave up, concave down, if the function has asymptotes, if the function is undefined, end behavior, right? Infinite limits, limits at infinity. We talked about all that stuff. So I've got here written out just a list of some key things that we look for when we are trying to graph a function, and we're trying to graph a function that we know is differentiable. So we'll kind of be going through this list, and at the bottom here I've got how to do each little key point here. So for instance, this first one is asking when is f of x positive, 0, negative, when is it undefined. These are all basic questions, right? Basic questions, and how to answer that is essentially to perform a sign analysis on f of x. And we've done that in class. Perhaps this vocabulary, I know I've used sign analysis. I've mentioned it a few times. That's what it's called when when you do something like this, and you oh, it's undefined here, it's positive, 0, negative, positive. This is doing a sign analysis. So without further ado, let's get started. Let me undo that. Okay. So our example for today is f of x equals 1 plus 1 over x minus 1 over x squared. Now, the first thing we want to do here is stop erasing. That's the first thing I want to do. But so I'm going to find the vertical and horizontal asymptotes. Okay, so we've got f of x is equal to 1 plus 1 over x minus 1 minus x squared. Now, to find the vertical and horizontal asymptotes, we're looking at 6 and 7. So does f of x have any vertical asymptotes? Well, remember that vertical asymptotes correspond to infinite limits, right? So when we're talking about a vertical asymptote, we're looking to see if you've got this limit. Let me actually blow this up. If we're looking at infinite limits, and you're looking to see if the limit as x approaches some finite number from the left or from the right is equal to plus or minus infinity. Okay, so because this function, f of x, is actually a rational function, let's rewrite f of x as, so first it's 1 plus 1 over x minus 1 over x squared. But we can also rewrite it to have as a rational function. So we'll get a common denominator, and we'll have x squared plus x minus 1. Okay, so we'll go back and forth between which form we'll use, right? Because these are both equivalent, right? 1 plus 1 over x minus 1 over x squared is the same thing as x squared plus x minus 1 over x squared. Sometimes it'll be more convenient for us to use this form. Sometimes it'll be more convenient to use that form. Now, in determining, okay, so what we want to do is we want to figure out when f has a vertical asymptote. So it's going to be better for us to use this form because f is a rational function. So f is a rational function. So f has asymptotes where f is undefined. F has vertical asymptotes where f is undefined. And for us, this is going to be when x equals 0. So looking here, the domain of f is going to be negative infinity to 0 union 0 to infinity. Okay, and we expect to have an asymptote at x equals 0. We don't know the behavior. We don't know if x is going, right, because you could have, so here's what I mean when I say we don't know the behavior. These are 3 different cases of having an asymptote at x equals 0. Okay, so here's my asymptote, right? My asymptote is the y-axis in each of these cases. But now I don't know if my function looks like this, if my function looks like this, if my function looks like this, right? I also could have it where my function is like this. So each of these corresponds to a different responds to a different case, right? This one here is limit x approaches x approaches 0, f of x equals negative infinity. And this one is limit x approaches 0, f of x equals plus infinity. This one is the limit as x approaches 0, f of x does not exist, right? Because the limit from the left is not equal to the right. And we have the same for this graph right here. Okay, so I need to figure out, what does my graph look like, right? Do we have, what is the behavior? That's what I need to figure out. So let me go ahead and do a sign analysis. So doing a sign analysis is not only going to tell me where my function is positive and negative, but it's also going to give me the type of infinite limit that we have. Okay, so let's see here. So I'm going to do a sign analysis, and I can do, so let's see here, so let's do a sign. Let me actually make this smaller. Let's do a sign analysis of f. Okay, so I know that f of x is equal to, now I'm going to use this format, x squared plus x minus 1 divided by x squared, because since it's factored, I just know I need to make one line for my numerator, which is x squared plus x minus 1, and I need another line for my denominator, and then I'll have a third line. Actually, I can try to do this a little neater. So I'll have one line for my numerator, one line for my denominator, and then one line for my function f. Okay, so this is going to be for x squared plus x minus 1. This one is going to be for x squared, which is my denominator, and this is going to be for the quotient, x squared plus x minus 1 over x squared, which is the same thing as my f of x. Okay, now for x squared, this one is probably the easiest, because at 0, my function is 0, x squared is 0, and x squared is positive everywhere else. Okay, now what about this x squared plus x minus 1? I need to determine when it's positive, when it's negative, when it's 0. Okay, so how am I going to do that? So here's a question. When is x squared plus x minus 1 positive, negative, 0? Well, I can't factor it easily, so I'm just going to actually use my quadratic formula. That's going to be my first step. So x equals negative 1 plus or minus square root negative 1 squared minus 4 times a is 1 times c is negative 1. And then all of this divided by 2a. Okay, so we'll get, this is equal to negative 1 plus or minus square root of 5 over 2. Okay, so this means I've got a parabola, and the parabola is 0. The parabola is 0 at negative 1 plus root 5 over 2 and negative 1 minus root 5 over 2. Okay, now the question, now I don't know if you remember how to graph parabolas, but so we're looking up here. So here's our parabola. We're trying to graph x squared plus x minus 1, and we know that it's equal to 0. Zero's at negative 1 plus square root 5 over 2 and negative 1 minus square root 5 over 2. Now clearly this number is clearly negative, clearly less than 0, because I've got negative 1 minus root 5, right? So that's less than 0. So the numerator is less than 0, so this whole number is less than 0. My question now is this number less than 0? Greater than 0, right? Because if I'm trying to draw my number line, I know I've got 0. You see I've got this 0 here that I'll have. And I've got over here some negative number. So I can go ahead and put in my negative 1 minus square root 5 over 2. But I need to know where to put negative 1 plus square root of 5. Does it go right here? Does it go right here? Does it go over here? Right, so I've got to figure that out. And here's how I do it. So I'm going to put negative 1 plus square root of 5 over 2 versus 0. And then I'm just going to actually perform my algebraic steps. Multiply both sides by 2. Negative 1 plus root 5. I'm going to add 1 to both sides versus 1. And then now I can square both sides because we're dealing with two positive numbers. So I'll say 5 versus 1 squared. So, so this is bigger. So this is bigger, right? So this is 5 is bigger than 1. So square root of 5 is bigger than 1. So negative 1 plus root 5 is bigger than 0, right? So negative 1 plus root 5 over 2 is bigger than 0. So negative 1 plus root 5 over 2 is bigger than 0. Okay, so let's go ahead and put it over here. So we've got negative 1 plus root 5 over 2. Now, I still need to know, remember, I need to know when x squared plus x minus 1 is positive, negative, when it's 0. So far, I know that it's 0 at the roots. And because this is a parabola and it's facing up, right, it's facing up because the leading coefficient is positive, I know that the parabola has to be of this form, right? So if it has two intercepts, that means that the function is positive outside those intercepts. So I can go ahead and fill this in. And negative inside those intercepts. Okay, so now I am ready to combine my information. Okay, so now how am I combining it? Well, I bring down the pertinent information. Remember, the pertinent information is going to be when your separate functions are equal to 0. When x is equal to negative 1 minus root 5 over 2, f of x is equal to 0. The same thing for negative 1 plus root 5 over 2. However, when x is equal to 0, f of x is undefined. So I put an undefined there. And to the left of negative 1 minus root 5 over 2, we'll have a positive divided by a positive. So that'll be positive. To the right, we'll have positive divided by a positive. So that'll be positive. Between negative 1 minus root 5 over 2 and 0, negative divided by a positive. That'll be negative. And the same for the other interval, negative. Okay, so I am able to tell, let me just clear this up a little bit. Right, so after doing my sign analysis, so conclusion, f is undefined at x equals 0. It is positive on negative infinity to negative 1 minus root 5 over 2, union negative 1 plus root 5 over 2 to infinity. It is negative on negative 1 minus root 5 over 2, comma 0, union 0, comma negative 1 plus root 5 over 2. And it is 0 at x equals negative 1 plus minus root 5 over 2. So from this sign analysis, I already have an idea of how my function, where my function fits on the graph. Let me go ahead and erase this. So this page, we're going to keep track of the overall graph. Now this process overall of sketching a graph takes a long time because there are so many steps. I'm going through it in very gritty detail, okay? And when you're doing it in the beginning, it's going to take you a long time too, but you'll get faster the more you practice. So I want to put that out there. Okay, so this is our f of x. Let me just make this a little bolder here. So just overall, I know it. So let's say this is negative 1 minus root 5 over 2. And this is negative 1 plus root 5 over 2. I know that my function is positive over here. So the function has to be somewhere over here. The function is negative, so it's got to be down here, right in between. I hope you see what I'm trying to do here. I'm trying to shade where the function is, right? And then it is positive after back here. So the function has to fit in the blue. F of x, the graph of f of x must be in the blue portions. Okay, and we already know, that f has an asymptote at 0. So let's go ahead and put in an asymptote. So we've got an asymptote at 0. So probably, I don't know, but so we know that the limit as x goes to 0, f of x is equal to negative infinity. How do we know that? Because we know that we have an infinite limit and f is negative, right? F is negative to the left and to the right of 0. So probably, since we know that f of negative 1 plus root 5 over 2 is equal to 0, our graph goes through here, and f of negative 1 minus root 5 over 2 is equal to 0. So the graph goes through this point right here, and we've got a negative, right, we've got an asymptote So our function is going to negative infinity. So we've kind of got part of our graph already. Okay, and all of this we got just from looking at the vertical asymptote. Now let's look at the horizontal asymptote. So remember, for horizontal asymptote, this is number 7. Horizontal asymptotes come from looking at the limits at infinity. So we need to look at the limit as x goes to plus infinity and the limit as x goes to minus infinity of f of x. So let's look at horizontal asymptotes. Horizontal asymptotes. Okay, so we'll say limit x goes to plus infinity of f of x is equal to the limit x goes to plus infinity. Now this time I'm going to use this format of f of x because it's easier. 1 plus 1 over x minus 1 over x squared. Now notice that as x goes to plus infinity, 1 over x goes to 0 and 1 over x squared goes to 0 even faster. So this limit is going to equal 1. Okay, since 1 over x goes to 0 and 1 over x squared goes to 0 as x goes to plus infinity. And the same is true for the limit as x goes to negative infinity f of x. It's also going to equal 1. So what this tells us is we have our horizontal asymptote. It's going to be y equals 1. And from before, we had that our vertical asymptote, x equals 0. Now, we can go in here and put in our horizontal asymptote at y equals 1. Okay. And we know that the long-term behavior of this function is going to be towards that horizontal axis. Okay, so we've done number 1, which is the horizontal and vertical asymptotes. Now, determine the intervals where the function f of x is increasing or decreasing. So this is number 2. So to find out when a function is increasing or decreasing, what do? Perform a sign analysis on the derivative of f. Okay, so f is increasing if f prime is positive, okay, and f is decreasing if f prime is negative. So of course this means we need to actually calculate f prime. So f of x, 1 plus 1 over x minus 1 over x squared. I'm going to rewrite this as 1 plus x to the negative 1 minus x to the negative 2, because then it is easier to see my derivative. Okay, so since f of x is equal to 1 plus x to the negative 1 minus x to the negative 2, f prime of x, just using the power rule, is going to be negative x to the negative 2 plus 2x to the negative 3. And so I know that I'm going to need to perform a sign analysis. So let me go ahead and rewrite this as 2 over x cubed minus 1 over x squared, right? Which now I'm going to combine it so that I can have a product of terms. So I'll have 2 minus x over x cubed. Okay, so I'm doing my sign analysis, and I know I'm going to need 1 for the numerator. I'll need 1 for the denominator, and then 1 where I put everything all together. Okay, so my numerator here is 2 minus x. My denominator is x cubed. And lastly, we'll have 2 minus x over x cubed, which is equal to f prime of x. Okay, so we can go ahead and put our zeros in. X cubed is the easiest because it is 0. at 0, and it'll be positive when x is positive, and negative when x is negative. Okay, what about 2 minus x? 2 minus x is going to have something special happen at 2. It's going to be 0 when x equals 2. And it will be negative when x is greater than 2, and positive when x is less than 2. Okay, so putting it all together, I know that my special points are 0 and 2. When x equals 2, f prime of x equals 0. When x equals 0, f prime of x is undefined, right? Because you can't divide by 0. And then to the right of 2 will be f prime of x is negative. Okay, and to the left, f prime is positive. Okay, so far, f is increasing on negative infinity to 0, union 0 to 2. F is decreasing on 2 to infinity. Right? So if we were to put in our sketch of f, here's 2, here's 0. Our function is concave down. Sorry, the function is decreasing. So we can put some decreasing arrows, increasing here, and increasing here. Oh, you know what? I made a mistake. Because for x cubed is positive here, and x cubed is negative when x is negative. So that should be negative. Now, that's going to impact my f prime. So my f prime is going to be negative on this interval. And my f is not going to be increasing. It'll be decreasing. Okay, so this tells us, for instance, that we know that 2, so since f prime of 2 equals 0, 2 is a critical point of f. Since f is increasing when x is less than 2 and decreasing when x is greater than 2, f must have a local max at 2. So moreover, f has a local max at 2. So let's find the local maximum value. So f of 2 is going to be 1 minus plus 1 over 2 minus 1 over 2 squared, which is going to be 1 plus 0.5 minus 0.25. So we'll have 1.5 minus 0.25, which is going to be 1.25. So f has a local max value of 1.25. This local max occurs at x equals 2. Okay, so in fact, I believe we are answering find the local max and minima values as well. So let's go over here. So we've got our local max. The local max is 1.25. F is increasing on, no, we needed to change this. It's increasing on 0 to 2. And it is decreasing on negative infinity to 0, union 2 to infinity. Okay. Okay, so how can we put this in our graph? Well, how can we use the fact that we have a local max equals 1.25 and it occurs at x equals 2? From the graph that we've shown, since our function has to be within the blue area, we actually don't even have to do any computations. We can just go ahead and say that 2 has to be bigger than -1 plus root 5 over 2. And since this is y equals 1, our 1.25 should be somewhere like up here. So this is our local max. So since it's a local max, the function should look something like that. And then nowhere else is there a local max. Okay? Now, our function is increasing on 0, 2. Let's see if that makes sense. From 0 to 2, the function is increasing. So we can actually go ahead and fill this in. It's increasing from 0 to 2. The function is decreasing from -infinity to 0 and from 2 to infinity. Decreasing from 2 to infinity. So we're going to be decreasing from 2 to infinity and decreasing from -infinity to 0. Now, here's the issue. Because you might say, hey, why can't we just go ahead and fill it in? The issue is because you've got two ways to decrease. You could decrease like that, right? Or you could decrease, let me show you another way you could decrease. You could decrease like that. Now, what's the difference between these two? Right, because both of these would fit, both of these versions would kind of fit in the left-hand side, right? Because, like, here's your asymptote at x equals 0. The difference is concavity. So concavity is what's going to allow us to not guess about what the graph looks like, but to be certain. Okay, so let's go ahead and get ready to do D. So we want to find the intervals of concavity. And in order to find the intervals of concavity, you need to perform a sign analysis on f double prime. So we did this. Okay. And now I put here this little symbol. Sometimes it's helpful to know or to remember. Right? Symbol helps remind you. A smiley face. Right? That little smiley face tells you your derivative is positive, so you're concave up. If your derivative is negative, then you're concave down. Okay, and you need the second derivative, so that's why it's got two little marks for the eyes. So let's go ahead and get ready to calculate our second derivative. Okay, so we need f double prime. So I'm starting off with f prime of x. What is f prime of x? This time I'm going to use this version, negative x. So I'm going to use this version of f prime of x, right? Because if I use this bottom version here, I'm going to need to do the quotient rule. And I can just do the power rule if I use this version of f prime. So I've got negative x to the negative 2 plus 2x to the negative 3. Negative x to the negative 2 plus 2x to the negative 3. Now, I can go ahead and take the derivative to get the derivative of the derivative gives me my second derivative, and I'll have 2x to the negative 3 minus 6x to the negative 4. Now, I'm going to need to perform a sign analysis, so I need to know when the second derivative is positive and when it's negative. Okay, so let's go ahead and write it as a fraction. 2 over x cubed minus 6 over x to the 4th. And I'm going to factor out 2 over x. No, I'm not. So let me do this instead. And here's the reason why, because I was going to say I'm going to factor out 2 over x cubed times 1 minus 3 over x. But then I would have to have 1 for 2 over x cubed and a number line for 1 minus 3 over x. And in my head, it's a lot easier if I write it like this. Right, and I've got a number line for 2x minus 6 and a number line for x to the 4th. Right, so that's how I determine how to rewrite the function that I'm trying to perform a sign analysis. Okay, because it's whichever one is going to end up being easier for me to work with, kind of. Okay, so I've got my 2x minus 6, my x to the 4th, and then I'll have my last one, which is 2x minus 6 over x to the 4th, which is f double prime of x. Okay, so for 2x minus 6, 3 is going to be the 0, and this is going to be positive if x is bigger than 3, negative if x is less than 3. And then for x to the 4th, it'll be 0 at x equals 0, positive everywhere else, right? Because x to the 4th is always positive. And now combining it, I know I've got special stuff happening at 0 and 3. When x equals 3, f double prime is equal to 0. And when x is equal to 0, f double prime is undefined, right? Because you can't divide by 0. Now, to the right of 3, it'll be positive. To the left of 0, it'll be negative. And in between 0 and 3, it will be negative. So this tells us that f is concave up on 3 to infinity, and f is concave down on negative infinity to 0, union 0 to 3. Okay. Let's see if we can put this information into our graph. So we're concave up. So f is concave up. This is on, what do we have? Concave up on 3 to infinity. 3 to infinity. And concave down on negative infinity to 0, union 0 to 3. Okay. So I need to put here a point for 3. Now, f of 3. So here's the issue. The issue is f of 3, is it up here? Is it above this asymptote? Or is it below the asymptote? Okay? Because that's going to determine how the function approaches y equals 1. Is it going to approach it from below? Or is it going to approach it from above? So I need to figure out what is f of 3. Okay, so f of 3 is going to be 1 plus 1 over 3 minus 1 over 9. So this is going to be 4/3 minus 1 over 9, which is going to be 12 over 9 minus 1 over 9, which is 11 over 9, which is bigger than 1. All right, so it's going to be above. So I am expecting you to be able to do computations like that, okay? So I'm concave down. So I know that this is, this point was 1.25, and now f of 3 is 11 over 9, okay? So we're concave down, and then it starts to be concave up. This is probably, it's kind of hard to see. But essentially, what we're doing is so this is concave up and decreasing. And we are hooking this up, right? So this is concave up and decreasing, and we're hooking it up with something that is concave down. Okay, but it's all happening, all of this activity is happening in a very narrow window, okay, because we've got this asymptote. And we can ask ourselves, hey, when is f of x equal to 1? Because for all we know, it could be that this is our asymptote, y equals 1, right? And then here's 0, here's 3, here's our local max, right? And then we come a little bit, and it changes concavity. And it could be that it goes like that, right? But the graph doesn't go below the asymptote. And let's verify by asking ourselves, when is f of x equal to 1? So to solve when f of x is equal to 1, that's solving 1 plus 1 over x minus 1 over x squared is equal to 1. And it's actually better for us to use, now that I think about it, it'll be better for us to use this version, x squared plus x minus 1 over x squared. So I have x squared plus x minus 1 over x squared equals 1. Okay, so I'm solving this, and I'm going to say, therefore, let me write a little smaller. X squared minus x plus x minus 1 over x squared equals 1. So cross multiplying, x squared plus x minus 1 equals x squared. Okay, so I can subtract x squared from both sides and get x minus 1 equals 0, x equals 1. So the only time f of x crosses, I think I'm writing this sloppily. So here's what I want to say. I want to say, so since f of x equals 1 happens only when x equals 1, f of x, the graph of f of x crosses the asymptote only once. Only once at the point 1 comma 1, which is this point right here. So that's 1. Can we zoom in? Let's zoom in. So we're crossing one time, and that's when x equals 1. We've got our local max here. We've got an inflection point. Do you see how 3 is an inflection point? 3 is an inflection point because the sign of f double prime is changing. It changes from negative to positive. So let's actually put this in our little. 3 is an inflection point of f of x because because f double prime changes sign from negative to positive, right? It was negative, now it's positive. And whenever your second derivative changes sign, you have an inflection point. So that, I think, was actually, here, find any inflection points. We found the inflection points, right? So when is it concave up? When is it concave down? Any inflection points, we found those. When is f positive, 0, negative, undefined? That was kind of the first thing we did. We did a sign analysis. And let's put it all together. So we've got an inflection point. We've got an inflection point at 3. We've got a local max at 2. local max occurs. Right, so this is a critical point at 2. At 1, this is when the graph of f is crossing the graph of f, crosses the asymptote. And we've got an intercept. What is that? That is a x-intercept. So we've got all these key points here. So there's kind of a lot of action that happens over here because we do have an inflection point. We change concavity. Right over on the left-hand side of the graph, the only thing we know is that, so we know that our function is going to be concave down, okay, and it'll be decreasing. So if the function is concave down and decreasing, so f is concave down and decreasing on negative infinity to decreasing negative infinity to 0. So, and remember, the function only crosses the y-asymptote once. So we've only got one way we can kind of draw this, which is like that. Right, so we've drawn, so you can kind of see our function is decreasing, it's concave down. Then the function is increasing, but it's still concave down, increasing, 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 concave down, increasing, decreasing, concave down, decreasing, concave down, decreasing, concave up. Okay, so I think I want to just highlight just a tad bit more for us to describe what's happening. So 3 is important, 2 is important, 0 is important, okay, in terms of concavity. So the function, so on 3 to infinity, our function is decreasing and concave up, okay, on 3 to infinity. From 2 to 3, our function is decreasing concave down. From 0 to 2, the function is increasing and concave down. Okay, the function is decreasing concave down back here. On negative infinity to 0. Okay, so you can see the progression in terms of the derivatives, the first derivatives, the second derivatives, all of that. Okay, and in fact we can put in here the function is positive, right? The function is positive, the function is positive, here the function is negative, here the function is negative, and here the function is positive. And so what I'm keeping track of by doing this is I'm keeping track of, right, positive and negative. This is telling me about the sign of f. Increasing, decreasing. This is telling me about the sign of f prime. Concave up, concave down. This is telling me about the sign of f double prime. Okay? And when f prime and f double prime are equal to 0, you have a change in f, a change in f prime, and a change in the sign of f double prime, right? So remember, the key thing is that special things happen when good things happen when things are equal to 0, right? Interesting things happen when other things are equal to 0. That's essentially what we're doing here for this sketching a graph, is we're just looking at when is our function equal to 0, because that'll tell us when it's changing signs. When is our first derivative equal to 0, because that'll tell us when the first derivative is changing sign. When is our second derivative equal to 0? That'll tell us when our function is changing concavity. Okay? All right. Thank you very much. Please practice this.